everybody, welcome back to this YouTube channel. Today we're going to be experimenting with the sun and the solar system. So before I experimented with the Earth by colliding planets and colliding moons and human-sized objects, turning the Earth to be tidally locked, and also put it in Eta Carinae B for some reason. So now, the sun now. And seeing what happens to the entire solar system, as you can notice. With the entire solar system in hand, we are going to be experimenting with the sun. So now, we're going to be adding a companion sun, since the first experiment is a binary star system. So now, we're going to be simply putting another sun, and seeing what happens. So 3, 2, we're going to pause this, 3, 2, 1, here it is, and now we're gonna give both suns a barycenter. So now they're not orbiting. So the suns are not orbiting each other. They're now orbiting a barycenter. I'm gonna make it so that all the planets are orbiting a barycenter because of this. So the barycenter is where the this is the barycenter, home, which is to mass the sun, and it is associated with each. So can you see if the planets survive? Now let's see. They're both orbiting the barycenter right now. Now the orbits are destabilizing. All orbits are starting to destabilize. And look, as you can notice, the planets have completely went unstable. The orbits are just out of control. The habitable zones are completely messed up, and just everything is completely getting out of control with this. And yes, this is just giving the sun another sun and giving it a barycenter. So if it's Universe Sandbox, it's most likely just Universe Sandbox, but apparently this is what happens if the sun had another sun in it. So this is the first experiment we're going to be doing with the sun. And here's the after results for the entire solar system. The orbits are out of control. Earth is almost completely gone. As you can notice, the sun just moved away slightly. Here's the Earth, completely and utterly frozen, -100 degrees. And the sun, and you should never have a binary star system like this. So in Universe Sandbox. So now that we experimented with this, we're going to be doing another experiment we're going to be resetting the solar system because of how much chaos has happened. And now, the second experiment is what happens if you throw a rogue star into the sun. I mean, rogue star passing by the sun. It's not like we're going to be hitting the sun, because really, why do we do that? And we're going to be using a red dwarf for the example, called Barnard Star. And it's now coming into the sun. It will take some time, so I will just be speeding up the day line and the days and the years. As you can notice, everything's normal with the sun and everything. Completely just utterly normal. See, the orbits are similar. Barnard Star is just coming in right now. Sedna's orbit is starting to get a little unstable right now, but it's kind of normal. Barnard Star is officially entering the solar system right now, and already the Kuiper Belt starting to see some and already we're starting to notice small destabilizations with the Kuiper Belt now. Yeah, we can see a lot of destabilizations with the entire Kuiper Belt as it continues its journey. It continues to disrupt a lot of planets' orbits. Pluto's orbit is getting disrupted. A lot of the Kuiper Belt's completely out of control. And now we unpause it. Neptune and Uranus' orbit's completely unstable. They're almost completely stopping to orbit. Barnard Star is officially in Mercury's land now. So now, here we go. A lot of planets have left, and Barnard may be the closest approach, and all the orbits are completely messed up. Some of them just completely stopped orbiting and are flying by the sun. So here's a reminder, is that if a rogue star came extremely close to the sun, this happens. If the rogue planet comes leaving very close to the solar system, you will see that this happens. which can, and over time there will be some orbital restabilizations. However, right now the Rouge Star has disrupted a lot of the orbits so much that a lot of the planets now have extremely different orbits than what they used to. Remember the Earth being 1 astronomical unit away? Now it takes 1.2 years. This one now takes 5 months. Apparently all of the planets have small orbital disruptions. And you can see the habitable zone. Earth is still in the habitable zone, but Mercury's eccentricity has been increased, with all the planets' eccentricities going up because of Barnard Star. This is the second experiment. The third one is going to be the longest one, because we're going to be making sure the sun is going to get hotter and hotter as time goes on until it reaches a grand temperature of 1,000,000 degrees Kelvin. So now we're going to be setting the surface temperature up. The sun is now, let's give you a detailed journey as the sun increases and what is happening at the temperature. At a 5,800 degrees Kelvin, it is a high-class G-type G2V main sequence star. Right now, it is a G1 main sequence star. Now it's a G0 main sequence star. Now it has officially become a low-class F-type star. Earth has left the habitable zone. Mars is now in the habitable zone now. So this is the middle-class F-type stars now. It is now officially a high-class F-type star. Now it is a low-class A-type star. Sun is now white. Mars is officially inside the habitable zone right now. Earth is also out of the habitable zone entirely. Now, Mars is in the intersection of the habitable zone as the Sun becomes a middle-class A-type star. The Sun is now almost a high-class A-type star. Mars is out of the habitable zone entirely, so let's go to Neptune's orbit. The Sun is still increasing in temperature. It is now a low-class B-type star. It's a high-class B-type star. Now we're officially getting into the O-type star. Sun is now in low-class O-type star now. And it's getting hotter and hotter. Luminosity rise is 473. Now it's getting hotter. It is now officially a high-class O-type star now. All the planets are now shooting off due to the extremely high temperatures. The sun's getting hotter and hotter. It is officially a Wolf-Rayet star temperature. The sun's still we are not done. Our goal is now to give it to a 1,000,000 degrees Kelvin. Mercury and Mars have been destroyed by the sun's heat by now. And now we are 200,000 degrees Kelvin, 2/10 of the way there, or 1/5 of the way there. Earth is gone, so now it continuing to increase. Sun is now 300,000 degrees Kelvin. It is now officially hotter than even Wolf-Rayet stars at this point. It is now almost the same temperature as neutron stars now, and Jupiter is torrid now, 10,000 degrees. It is still it's hotter than even Kel 9. The sun is now almost. You can see Jupiter and Saturn have been destroyed. The sun is now 1,000,000 degrees Kelvin, at least more than 1,000,000 degrees Kelvin. And let's speed it up. What happens to Uranus and Neptune? Uranus is gone, and Neptune has been destroyed. So sun has turned 1,000,000 degrees Kelvin, and for fun, we're just gonna add a habitable planet to it. So let's put the Earth in this 1,000,000 degrees Kelvin sun. Let's go to whatever, and it's still gonna be in the habitable zone. So we're gonna set the orbital period to this. This is the almost where Earth is gonna be in the habitable zone, and you can see Earth is blue. The orbital period is longer, and everything is just completely on. And let's just increase it. Now the Earth is like in the habitable zone right now. So as you can notice, the Earth's temperature is, this is the temperate temperature on the Earth. 4,000,000 years. The orbital period is 4,000,000 years if the sun was that hot. You can notice how insane this is. 4,000,000 years. That's insane. And also, the distance is slightly less than half a light year away from the sun. So, if the sun was an O-type, was like 1,000,000 degrees Kelvin, for it to be in the habitable zone, it has to be over 0.4 light years away from the sun. That is insane. Imagine how hot this is. So anyways, that concludes the video. Make sure to subscribe if you learned anything new or if you had fun. So I'll see you later. Goodbye, everyone.